Hello, Mr. Claudia here, and today we are going to use probability distribution functions to calculate expectation, to make a prediction of what we expect the distribution to do. So for example, you already have an idea of what expectation is. Each time a soccer player kicks the ball toward a goal, he has a 3 out of 4 chance of being successful. If in a game he has 12 kicks on goal, how many goals would you expect him to score? Well, we know the probability of him getting a goal is 3 out of 4. So if he takes 12 kicks, I'm going to multiply that by 3 over 4. That's going to give me 9 goals. That's a prediction, right? Is he going to get 9 goals? No, but... Oh, prediction. But that's our best guess. This is a big thing in baseball, right? You keep track of the stats of how accurate someone is at hitting the ball, so we can make a prediction. Oh, they're probably gonna get on base this coming up because they haven't had so many. They haven't gone on base in a while. So the expected value is the average value that we should expect from a random variable over many trials of an experiment. And what we just did is we took the number of trials, 12, the number of kicks, and we multiplied it by the probability. So that's kind of our base formula, n times p. That's the number of times we expect the event to occur. We'll just put that in a little box here. So that's n trials, and p is the probability. Okay, I want to do a little investigation before we get to the next formula. And I like this investigation because it gives you an idea of how expectation works. So a magazine store recorded X, a random variable X, which is the number of magazines purchased by its customers in 1 week. So 23% purchased 1 magazine, 38% purchased 2, 21% purchased 3, 13% purchased 4, and 5%, those were the big readers, they actually had bought 5 magazines per week. So, okay, let's make a probability distribution table for X. Remember, X is the number of magazines purchased. So what's the probability that a customer is going to buy 1 magazine? Oh, it's 23%, or 0.23. 2 magazines, 38. 21, 0.13, and 0.05. That's my probability distribution table for this discrete random variable. That's what we did. This is like what we did in the last section. Now, 25 customers come into the magazine store. Write the expected frequency of obtaining each of the different values of X. Okay, so think of what we just did. There's you take the number of trials and you multiply it by the probability. So here, if I have 25 customers, then the probability, and the probability is 0.23, then I would expect 5.75 customers to purchase 1 magazine. So that was 25 times the probability gives me 5.75. Now, we can't have 0.75 of a person, but this gives us an idea, right? Of those 23, almost 6 of them are going to buy 1 magazine. We can do the same thing for my other entries in my probability distribution table. I'm having a hard time here today. 0.38 times 25, which is 9.5. 25 times 0.21, which is 5.25. 25 times 13%, which is 3.25, and 25 times 0.05, which is 1.25. Using a calculator, of course, to calculate all those things. So again, of the 25 people who come into the store, maybe 1 of them will buy 5 magazines. This is useful for our magazine store owner. He's going to know, in general how many magazines to buy based on how many people come in. Okay, let's figure out the average number of magazines sold per customer. So this customer, one customer comes in, sorry, 5 customers come in and buy 1. Then 9.5 customers buy 2, 5.25 buy 3. So if I want to find the average or the mean, I'm going to take each of these values and multiply it by the number. So the number of customers times the number of magazines. So this should give me the total number of magazines. And I'm going to divide that by, because I want the average, I need to know the total number of customers, which is 25. So I should, let me show my work this time. So I have 5.75. Oh, move this up. 5.75 plus 9.5 times 2 plus 5.25 times 3 plus 3.25 times 4 plus 1.25 times 5. And I divide that by 25. So 60 magazines sold, and I get 2.39 magazines. Again, this is a really useful stat. The magazine owner can predict that for every customer, they're going to buy just over almost 2.5 magazines. So they can make a prediction of how many magazines they need to buy for their magazine store to make sure that they don't run out. Now let's say 100 customers come into the magazine store. Calculate the expected frequency and then the mean. Well, this time, okay, so I have 100 customers, 100 trials, and the probability is 0.23. So I have 100 times 0.23. So probably 20, I would expect 23 customers are going to buy 1 magazine. Similarly, I multiply this by 100. So, you know, if I have 100 customers, probably 13 of them are going to buy 4 magazines. Now, if I want to find the average, I do the same thing I did last time. I take the expected frequency and I multiply by the value of x. So I have 23 times 1 plus 38 times 2 plus 21 times 3 plus 4 or 13. Oh boy, we're having a bad day. 13 times 4 plus 5 times 5. And I divide by 100 total customers. So I have 23 plus 38 times 2 plus 21 times 3 plus 13 times 4 plus 5 times 5. And then I divide that by 100 and oh my goodness, what do I get? 2.39. What do you notice? It's the same mean. It's the same average. It's the same expected value. So this is an important kind of proof. This is my kind of proof for what the formula that we're gonna see. The means are the same. In other words, the average number of magazines purchased by a customer entering the store is 2.39. The big finding here is that no matter how many customers enter the store, whether it's 25, 100, or just 1, this number stays the same. Because it's not based on the number of customers, it's based on the probability. It's based on the probability table. No matter how many customers. So that's our big takeaway from this lesson, the expected value. So instead of doing this every time where we make this table and we have to think it through, we have a formula. The expected value of a random variable x, also called the average or the mean, can be found by taking the sum of x times the probability that x is equal to x. Okay, let's decode this. First of all, lost my ruler. Oh, here it is. I'm going to just draw a little box around this. Okay, so the formula for expectation, which is another way of saying the mean, expectation, aka the mean. The formula is the sum, so we're going to add up for all outcomes the outcome, so x times the probability of that outcome. Oh, there it is. So this formula is saying to find the expected value, take each outcome, so all the things that x could be, so x is equal to 1, x is equal to 2, x is equal to 3, so, and multiply that outcome by the probability of the outcome occurring, and then add all those up. Add up for all outcomes, outcome times the probability of that outcome. And that's going to give you the expected value, which again is very useful. It's useful for the magazine store owner to know the average number of magazines they're going to sell per customer, because then they're able to make predictions about how many magazines they need to order. This is a great thing. Think about if you're running on the prom committee, you want to know what's the expected number of people who are going to buy prom tickets, blah, 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 things like that. Okay, now one of my favorite examples is the one we're going to do now. The finite insurance company has analyzed its claims per car insurance policy. Okay, so first of all, let's just talk about how insurance works. So insurance is something you pay for and you get a product in return, right? I pay every month insurance for my car, insurance for my home. What is the product? Why am I paying this money? Well, if something goes horribly wrong and I get into a car accident, I can make a claim and the insurance will pay me some money to repair my car. So I'm paying this money and I might never get anything back, but if something does happen, they are going to help me in this catastrophic event. So a lot of people, you're required in Canada to have insurance on your home to prevent it from, protect it from fire, and you're required to have insurance for when you drive to protect you and other people and the vehicle from if there's a horrific car crash. If you do have to, if something bad does happen, you have to file a claim. That's what insurance speak for when they claim is when they pay you money. So this is the information for a car insurance policy. A policy is just kind of the program, I guess, or so this is at the insurance company. They've analyzed all the claims. So 0 means no claims. So this means that you pay the people who paid the insurance and they didn't have to ask for any money back. They didn't get into a car accident. The probability of that happening is 70%, 0.7. So it's very high. Most people, they have no claims. What's the probability of somebody having a $1,000 claim? It's 20%. So every year they have to pay out that much. What's the probability of having a $5,000 claim? 5%. So it's a big claim, but it's very rare that happens. What's the probability of a $10,000 claim? 4%. And a $25,000 claim? 0.01%. The insurance company has to do these. This guy probably totaled this car. What's the probability that someone totaled their car? It's very low, but there are going to be a few customers that have that every year. So the insurance company is interested in the expected amount of money that they have to pay for each policy. Remember, policy is the programs. Like everybody who signs up for insurance has a policy. So each customer is a policy. So we want to know the expected amount of money that the insurance company has to pay. So we're going to use our expectation formula. This is on your formula sheet. Let me just get your formula sheet out. I also find this formula is forgotten. So if you're ever forgetting, what is expectation? I don't remember doing this because you remembered all the other stuff, but not this. It's in your formula book. add up for all outcomes, the outcome times the probability. So in this case, this is the outcome, this is the probability. So I take 0, multiply it by the probability. Add it to 1,000, multiply it by the probability. Plus 5,000, multiply it by the probability. Plus 10,000, multiply it by the probability. Plus 25,000, multiply it by the probability. Whew, okay. And if I do this, I'm going to find my expected value. So the first number is 0. 1,000 times 0.2 plus 5,000 times 0.05 plus 10,000 times 0.04 plus 25,000 times 0.01. And my answer is 1,100. Okay, so let's interpret this number. So that's the expected amount that the insurance company has to pay out per person, per policy every year. Average claim or payout per person, or per policy. So think about what this means. Like, I drive every year. I haven't gotten into many accidents. So I have 0 claims, right? Most people have 0 claims. Some people have really big claims. Some people are in between. But on average, if you add up all of the claims, the average is $1,100 per person. Even though most people have 0, because of these big numbers, I think it skews it to 1,100. So if the part B, if the company charges all drivers $900 for their car insurance policy, what can you conclude about the insurance company's profitability? Well, $900 is less than the $1,100 average claim. Therefore, we would imagine the company loses $200 per customer. I just think this is really interesting. Like, you would never have really guessed unless you did the math, right? I'm paying all this money. I never make a claim, so the insurance company is making a lot from me. But if the insurance company analyzes the big picture, they see that $900 is not enough to cover their average claims, so they're actually losing money per customer, so they're going to go out of business. And even though I hate paying insurance and it's ridiculous, and it goes up sometimes, it's very high for you guys, for students, we don't want the insurance company to go out of business, because the insurance company is there to protect us if something goes wrong, right? If I get in a car crash and I learn that my insurance company's out of business, well then I have a broken car and all these medical bills. So there are people, insurance companies, who are literally, their job is to analyze all these statistics and numbers and try to predict how much they need to charge so that the company doesn't go out of business. And it can be a little morbid if you're offering someone life insurance, which is insurance in case something goes wrong and you pass away. Can you imagine? Someone has to analyze the probability of that. So there's a career option in what we're doing here. This job, which is a great high-paying math job, is called actuary. So that's something you might be interested in. Just food for thought. What are some ways that I know if somebody's going to have a higher chance of getting into a car accident? Well, if they're younger, statistically they're more likely to get into a car accident. If they're less experienced, they're more likely to get into a car accident. Some neighborhoods in Toronto have a higher probability of accident. So all of these things are factored into how much you pay to the car insurance company. Okay, let's keep going. The next part of this lesson, we look at fair games. This is similar. This is another neat application of expectation. So in gambling, we say that the expected gain of the player from each game they play is their expected return, or the payout, minus the amount it costs them to play. For a fair game, the expected gain is 0. So we'll show you how this works with an example. we have a game of chance where a player spins a square spinner labeled with the numbers 1, 2, 3, 4. So I just want to draw that for you. So I have some sort of box divided into 4. And then I have, I have some sort of arrow that I spin. And it's going to land on one of those 4 spots, labeled 1, 2, 3, 4. The player wins the amount of money shown in this table, depending on what number comes up. So if 1 comes up, they win $1, 2, 2, 3, 5, 4, 8. This is great. You win something every time. So determine the expected return of 1 spin of the spinner. So we want to find what we can expect the average person to walk away with. It's going to be some number between 1 and 8. I mean, some people get $1, some people get 8, some people get in between. So let's let Y denote the payout or the return for each spin. So what is the expected payout or the average payout? Well, I have to do this, I have to use my formula. Where's that formula sheet again? It's the outcome times the probability. So here the outcome is $1. The probability of getting 1 is 1 out of 4. Actually, the probability of each of these things we're going to assume is 1 out of 4. That's the probability that Y is equal to Y. So the expected value is going to be $1, which happens a quarter of the time, plus $2, which happens a quarter of the time, plus $5, which happens a quarter of the time, plus $8, which is happen a quarter of the time. So then I could solve this with my calculator, or I could factor out a quarter and solve it by hand. That would give me 1 plus 2, 3, 8, 16. So my answer is $4. That's the expected payout, or the average payout. That means that whoever's running this game, this is a useful thing to know. Every person who walks up to play this game is going to walk away on average with $4. Now, is everyone going to get $4? No. Some people are going to get 1, some people get 8, some people get 5, 2. But based on the probability, we know the expected payout is 4. Part B, what is the expected gain if it costs the player $5 to play the game? Well, this is where we talk about fair game. So $4 is my expected return, minus, that's what they get, minus what they paid, which is $5 cost to play. And so their expected gain is negative $1. They're $1 down. So that's why we call this an unfair game. Every player who plays, on average, is losing $1. It's now, does everyone lose $1? No. Some people go, they win $8, they paid $5, so they walk away with $3. Some people, walk away with $1, so they lose a lot more than $1. But the average is everyone loses $1. So we say it's unfair. For the game to be fair, these numbers would have to be the same, and the expected gain would be 0. So if it cost me $4 to play this game, then it would be a fair game. Part C, would you recommend playing this game? Would you recommend it to a friend? No way, because there is an average loss of $1 based on probability. However, if you wouldn't recommend it, why is it that people gamble? Then why do people go to the racetrack, or why do they buy lottery tickets if we know the cost to play creates an unfair game, or where the expected gain is a loss? People still play these games because they like it. So people play games of chance for the perceived chance of winning it big. I mean, think about it. If you control the cost to play and you know the expected return, you can control what your gain is going to be as the person who runs the game. So casinos do this, right? Casinos calculate the expected return of each of their games and then charges accordingly to make sure that they make money. And the casino is always going to win. It's always going to have, it's always going to make money from the game. But people still go to the casino. People still buy lottery tickets because they like to, right? It's a way to enjoy themselves, and you have a chance of really winning it big if you do get that kind of lucky number. So gambling is bad, and statistically it's stupid, or probability-wise it's stupid. But if you have $20 to spend, some people like to go watch a movie for $20 and eat popcorn. Some people like to go to a casino and play slot machines for a few hours for $20. So as long as we look at games of chance as a fun activity, then I guess even though I don't think it makes any sense, it's something that people do. I think when games of chance become an addiction, then it's definitely more problematic. So anyways, that's an interesting application of expectation, and also their insurance. Two interesting applications of this. Your homework is page 525, number 1 to 10, and just remember, the house always wins. The house always wins. Okay, good luck with that, and we'll see you next time.